Hey, welcome back. Here we start on chapter 3, Applications of Differentiation. Section 2, the mean value theorem. This is an important theorem. The mean value theorem, the section, you see, it follows from what is first called the Rolle's theorem. All right. So, um, continuing with the slide, we will see that many of the results depend on one central fact, which is called the mean value theorem. But to arrive at the mean value theorem, we first need the following result, Rolle's theorem. Okay? Let f be a function that satisfies the following three hypotheses. Hypotheses means conditions that these satisfy. Okay. 1. F is continuous on the closed interval a to b. So closed interval a to b, f is continuous. That is, you understand. So you have an interval ab above a or below a, wherever f has a position, takes a certain height, and then it continues without breaking. All right. Second, f is differentiable on the open interval AB. What does differentiable mean geometrically? It means the curve is smooth. There are no breaks, there are no pointed structures. All right. So the curve is smooth over AB. And the third requirement is f at A equals f at B. What does this mean geometrically? It means the height at A has to be the same as the height at B. In other words, let's look at a picture. Okay, here A and here is B, right? So you are continuous, you are smooth, you may be going up and down, but you end up at the same height that you started. You end up at the same height that you started. You see in each of these examples. Okay, so if you're first, so what are the three hypotheses? FB continuous on the closed interval AB, FB differentiable on the open interval AB, and F at A equals F at B. Then the theorem states there is a number C in open interval AB such that derivative at C is 0. So geometrically, what does derivative mean? It means the slope of your tangent at that number. All right. So let's look at the pictures again. At A, you have certain height. At B, you have to have the same height. What if you don't go up and down? You just go straight constant function. So notice you have a horizontal line segment. Of course, the slope is 0 here. At every point. So every point you got slope 0. All right. In B, you are at A the height is this, right? And at B, the height is this. You are no longer a constant function. You go up a little bit, and then because you have to have the same height as F at A, you have to come down. So notice there is a point here, actually only one point, where you have slope 0. All right, horizontal tangent. So here is another example. Example C. At A, you have a certain height. Turns out you have to have the same height at B. Now your curve went up for a little while, then went down for a little while, and then came up to B. So it turns out you have 2 points. So you have 2 numbers for which the tangent is horizontal or the slope is 0. Okay. And the last example, at A you have this height, at B you have the same height. Instead of going up, you're going down. But because you have to have the same height, you have to turn around. So notice you get exactly one number where slope is 0. Okay, so the point of Rolle's theorem is if your starting point, starting height, and the ending height is the same, right, as in all these examples, and you are smooth, right? You're smooth, your graph is smooth, then you must have at least one number where you have tangent, um, horizontal tangent, at least one number where slope of the tangent is zero. You could have more numbers where the slope is zero. In fact, you could have every number, as in example A, where slope is zero. All right, but this you are not guaranteed. You are guaranteed at least one number where slope is zero. That is Rolle's theorem. Okay, there is a number C in AB. In AB, open interval AB means C has to be between A and B. C cannot be cap A, C cannot be B. All right, before giving the, so we looked at a few examples. Let's continue. Okay, so there is at least one point C, FC, on the graph where the tangent is horizontal and therefore derivative is zero. Rolle's theorem is plausible. Plausible means it's quite probable. It's well, it could be true, but the proof is some bit of work. All right, to to find the actual proof, go through the textbook, you will find the proof, but I'm not going to go over the proof, so let's continue with an example. All right, what is a good use of the Rolle's theorem? Here is an example. Prove that the equation x cubed plus x minus 1 equals 0 has exactly one root. Has exactly one root. So notice these words are rather clever, right? What are they saying? Prove it has a root and then prove that there is no other root. You understand? So has exactly one root means you must prove that there is one root and then you must prove that there cannot be any other root. Okay? So first we are going to use the intermediate value theorem to show that a root exists. Well, remember intermediate value theorem, you need two numbers where the value is negative, where value at one number is negative, value at the other number is positive. Okay, so somewhere in between you will hit zero. So this problem, the question is not giving us us any x values, so we have to eyeball it. We have to think a little bit. Look at that. When x is 0, these two are going to go away, only negative 1 will survive. So f at 0 is negative 1. It's a negative number, less than 0. Now again, just eyeball it. If x were 1, then you have 1 here, and minus 1. So 1 survives, which is a positive. So between 0 and 1, so at 0 you're negative, at 1 you're positive. So between 0 and 1, you will hit 0. So why? Because f is a polynomial, therefore continuous. So the intermediate value theorem states there is a number c between 0 and 1 such that f at c is 0. What does this tell me? Actually, it tells me that we have one real root. We found one root. Now we want to prove that we cannot have more than one root. All right. To show that the equation has no other real root, we have to use the Rolle's theorem and argue by contradiction. Okay. Suppose you had two roots, a and b. All right. Fa is 0, fb is 0. Since f is a polynomial, you can find its derivative. It is differentiable on open interval ab and continuous on closed interval ab. Thus, by Rolle's theorem, look, FA and FB have the same height, 0 height. So somewhere in between, you must have slope 0. That is, Rolle's theorem says there is a number C between A and B such that derivative of f at C is 0. Now let's look at the derivative. How did this come? Look at f, x cubed plus x minus 1. So when you take its derivative, the 3 comes down, 3x squared, and this gives you a 1. So that's all. f prime at x is 3x squared plus 1. Notice x squared. X squared means what? You will always be either positive or at worst 0. So 3x squared, the worst it can get is 0, or it will, after that it will only go up, and you are adding 1. So f prime will always be greater equals 1. That is, f prime can never be 0. If you're always above 1, you can never be 0. So this gives a contradiction. Contradiction means what? We first assumed there were two roots, A and B. So this approach of proving something is called by contradiction. Okay, proof by contradiction. We assumed something would happen and we encountered a problem because we wanted to find some C where f prime would be 0. But well, you cannot find. So that's a false statement. So why did we hit a false statement? Because we assumed something that was not true. What does that mean? We cannot find any other root. What does that mean? This polynomial has exactly one root. Okay, so I will stop my this video here and continue.